Hey there. We'll get started here in a couple minutes, but I'm glad you could join me tonight. We've got 59 people here, so that's terrific. Very glad to see it. So if you haven't already done so, please sign into Google. That'll give you a chance to go ahead and add some comments. I'll try to add a comment right now, see if it's going to work. So I've got a person from DePaul as well. Okay, all right. So we're going to take a look at the exam from last semester. So I hope you can hear me just fine. If not, say so, please. I am going to post this on the usual location on my channel, assuming all the technology works properly. But when we're finished today, we should be able to do that. So indeed, it should be there. Well, you know, we're having an issue this week with the teaching assistants. So I've decided to do the live broadcasting to kind of make sure that we stay on pace with our course. We're not supposed to do it during the regular day because that's when the teaching assistants are picketing. So yeah, I'm happy to do this here. Greetings from Hawaii. Well, good to have you from Hawaii. Hope this is a good experience for you. And again, we'll get started in a couple minutes once we hit 9 o'clock on my clock here on my computer. But hopefully it says welcome UIC students. Unfortunately, my image is in mirror, so it looks a little strange. But I assume you'll tell me that it looks wrong if that's the case. So, all righty. I think I'll start writing our first question. If you have an answer, you can go ahead and put it in the comments. Oops, try to get it. There we go. That's pretty good. So here's our first question. We are looking at the geometric series, the sum as k goes from 1 to infinity of a times r to the k. So you'll notice what that looks like. This, of course, when k is 1, what do we get? We get a times r to the first, plus when k is 2, we get a times r to the second. When k is 3, a times r to the third, plus dot, dot, dot. I really suggest when you're given something in this form to write it out like that so you've got an idea. So here's the first question I'm going to ask and see if you can answer it in the comments. So here's a question that we'll look at. So we'll say this series will converge when what? See if you can fill in the blank, and we'll take a look at it to see what we have. When will that series converge? What must happen? Give a minute to think about that. First suggestion is when r is less than 1 is what we're getting. Second suggestion we're getting is -1 is less than r is less than 1. And then we're getting various versions of this. Absolute value of r is less than 1. And sure enough, we have some correct answers. This is what we need. That could be correct. That could be correct. Please remember, in a geometric series, if r equals 1, it's going to diverge. If r equals -1, it's going to diverge. And that's a little bit different than our case of the ratio test. If we have the ratio test, if r equals 1, if that limit equals 1, the test is inconclusive. So here's the next question we have to ask, namely, assuming this converges, so remember we have the sum as k goes from 1 to infinity of a times r to the k. Make sure you can read that. Assuming this converges, what does it converge to? So go ahead and put that in the comments. We'll take a look at it. And we'll take a look. Getting two different sets of answers. We're getting a over 1 minus r and ar over 1 minus r. Let's look at them both. We're getting this answer, and we're getting this answer. So think about it. Which one of those two do you think is going to be right? And looking at the comments, I think I'm glad that mathematics is not a democracy. Because our rule is for a geometric series that converges, so if the absolute value of r is less than 1, the infinite sum of the geometric series, let's write this on a new piece of paper, just so we can see it clearer. So I will say, if the geometric series converges, if the geometric series converges, what does it converge to? It will converge to I like to say first over 1 minus ratio. That's our value. And the question gave us what? It was the sum as k goes from 1 to infinity of a times r to the k. Again, let's list our terms. If k is 1, a times r to the first. K is 2, a times r to the second. K is 3, a times r to the third, plus dot, dot, dot. Again, we're assuming it converges, so it's got to be first over 1 minus the common ratio. To get from here to here, the common ratio, of course, is r. But this is the first. So if I take first over 1 minus ratio, first over 1 minus ratio, the answer I get is the first term here is ar over 1 minus the ratio. So you've got to be careful. We, of course, recognize this form often, a sub naught over 1 minus r, but a sub naught corresponds to the first element in the list. So make sure you list all those out as you go ahead and do your analysis on that type of series. All right. So let's take a look at what we have next. We're going to look at a limit comparison test. So let's see what that looks like. We are going to say that we're going to examine the sum of a sub k and the sum of b sub k. And we want to go ahead and we want to use the limit comparison test, use the LCT. So the first question we want to recognize, and b sub k must have positive terms eventually. But let's just kind of keep that in mind as we're looking at this. So eventually beyond some n. But let's just go ahead and think of it in terms of positive values. Now, we take a look at this limit. We look at the limit as k goes to infinity of a sub k over b sub k equals L. And we will say that either both series converge or both series diverge. Either both series converge or both series diverge when L is what? So if you could go ahead and put in something in the comments and tell me what L is going to have to be for this to converge, we'll take a look at it and see what we have. So I'll give you a minute to do that. Well, basically, I'm telling you to use the limit comparison test here. That's going to be our analysis. When in doubt, it's typically safer to use the limit comparison test. But you're right. Sometimes you can use the direct comparison test as well. All right. So indeed, L's got to be between 0 and infinity. Most of you are recognizing that. When we see that, we're going to have a situation where both series are of the same type. So if sum of b sub k converges, so will sum of a sub k if L is nice. If sum of b sub k diverges, so will sum of a sub k if L is nice, as in between 0 and infinity. All right, take a look at an example. Here's our next case that we're going to examine. We're going to look at 2/3 minus 4/9 plus 8/27 minus 16/81 plus dot, dot, dot. So the first question I'm going to ask you to do is express this in sigma notation. Can you do that? Question A, express in sigma notation. That's going to be difficult for us to do. Question B, I believe it converges. So if so, what does it converge to? What does this converge to? So try that. I'll take a look at the comments to see if we are heading in the right direction. So go. We're saying either both series converge or both series diverge. Yes, right. That's right. I should have said that. Okay, seeing lots of things on our potential for the sum. I hope it's obvious that we have a geometric series. As we go from this value to this value, from 2/3 to -4/9, we multiplied by -2/3. From -4/9 to +8/27, we're multiplying by -2/3. So the common ratio here looks like it's going to be -2/3. Let us go ahead and express that in summation terms. What do we have? Common ratio of -2/3. Well, we're starting with 2/3. So I could say 2/3 times -2/3 to the k, as k goes from 0 to infinity. If k is 0, -2/3 to the 0 is 1. I start with 2/3. Then k is 1, 2/3 times -2/3, -4/9, etc. So that's one way for us to do it. There are others. What does this converge to? Well, our common ratio is -2/3. The absolute value of the common ratio is less than 1, so the geometric series converges. What does it converge to? It equals the first term over 1 minus the common ratio. What's the first term here? Looking at our numbers here, the first term is 2/3. Over 1 minus the common ratio is -2/3. So we have 2/3 over 1 minus -2/3, which is 2/3 over 1 plus 2/3, 2/3 over 5/3, which I believe is equal to 2/5. All right. Let's take a look at our next question. We're looking at a sequence. Remember, a sequence is an ordered list of numbers. A series is an infinite sum. So can we keep those concepts straight? That's challenging for us. But here we go. I'm going to say a sub 1 is 2 over 2. We'll say a sub 2 is 3 over 5. We'll say a sub 3 is 4 over 10. And we'll say a sub 4 is 5/17. So what I would like to have here is the following. I'd like to ask you to find a formula for a sub n. A sub n equals what? And then I want you to look at the limit as n goes to infinity of a sub n. So go ahead and give me an answer for a sub n. Go ahead and give me the limit as n goes to infinity for a sub n. I will take a look at this. Art is telling me the answer key was wrong. Okay. All right, we can certainly add that to our discussion. Looking at an alternating harmonic series. Again, the question is, can we see what a sub n is? Can we see what it is going to converge to? Not seeing a whole lot on there. Okay, now we have an answer. So you'll notice that the denominators 2, 5, 10, and 17 are interesting. The numerators 2, 3, 4, 5 are consecutive. But you'll notice 2 is 1 more than 1. So I think the numerator is always n plus 1. If n is 1, the numerator is 2. If n is 2, the numerator is 3. If n is 3, the numerator is 4. If n is 4, the numerator is 5. So I feel good about that one. Now the denominator, what is that going to be? 2, 1 plus 1. 5 is 4 plus 1. 10 is 9 plus 1. So I believe it is n squared plus 1. So I think we have our numerator of n plus 1 over n squared plus 1 is our a sub n. Now, what is the limit as n goes to infinity of a sub n? Well, maybe you could see the answer right off the bat, but let me go ahead and prove it. I'm going to divide top and bottom by n. So we'll say the limit as n goes to infinity, actually by n squared, of n plus 1 over n squared plus 1. Divide the top by n squared, divide the bottom by n squared, which equals the limit as n goes to infinity of n over n squared plus 1 over n squared divided by 1 plus 1 over n squared. And you'll notice the top goes to n over n squared. That's 1 over n. That's going to go to 0. 1 over n squared going to 0. 0 plus 0 over 1 plus 0 equals 0. So I believe that's what we have there. I have someone ask me to go a little slower. Why did I divide by n squared? Well, that's the highest power of the denominator. So when we're doing these kinds of problems, that's a good suggestion. Divide by highest power of denominator, or highest power of the bottom. Now, another strategy you could use is to go ahead and use L'Hopital's rule. So you could take x plus 1 over x squared plus 1, which I noticed someone just said in the notes here. Indeed, you could take the derivative of the top and the derivative of the bottom and see how the limits go there as well. So we can take a quick look at it from that strategy. So if I'm going to say that I have a sub n is n plus 1 over n squared plus 1, and I want the limit as n goes to infinity of a sub n, which is the limit as n goes to infinity of n plus 1 over n squared plus 1 is the same as the limit as x goes to infinity of x plus 1 over x squared plus 1. And notice the top goes to infinity and the bottom goes to infinity, which means L'Hopital is okay. When that happens, take the derivative of the top, take the derivative of the bottom, and see what your result will be. Limit as x goes to the root over the derivative of the bottom, which is the limit as x goes to infinity of 1 over 2x, which of course will equal 0. I like using x's instead of n's with L'Hopital. X's imply real numbers, n implies natural numbers. So it's not really fair to use a derivative with an n. All right. So the quick question we had in the comment a few seconds ago was to look at the alternating harmonic. So let me take a quick look at that before I jump into the next question on this test. So we are looking at the sum of -1 to the n times 1 over n as n goes from 1 to infinity. So the question is, does this converge or diverge? Now, what do we know? Let's remind ourselves of some things. First of all, what is the harmonic series? The sum of 1 over n without the sign flasher is the harmonic series. I like to use k's instead of n's typically, but you should be comfortable with both letters. The sum as k goes from 1 to infinity of 1 over k, which is the same as the sum as n goes from 1 to infinity of 1 over n diverges. This is called the harmonic series. We can prove that it diverges a couple different ways. Comparing it to an integral is a standard way. Looking at adding up whole strings of numbers, I kind of like this strategy. 1, a half, a third, a fourth, a fifth to an eighth, plus a ninth, plus a 16th. This is more than a half. This is more than a half. This is more than a half. This is more than 4/8 is more than a half. This is more than 8/16 is more than a half. So if you keep doing that, every bit is more than a half. So this, of course, has to go to infinity. However, if it alternates, so let's go ahead and take a look at this alternating. So we've got the sum as n goes from 1 to infinity of -1 to the n times 1 over n. To look at this, we should use the alternating series test. So we will say, appeal to the AST. So the absolute value of -1 to the n times 1 over n is just 1 over n, which is positive, which is good. 1 over n is decreasing. How does 1 over n compare to 1 over n plus 1? 1 over n is greater than 1 over n plus 1, or to think about it in terms of decreasingness, 1 over n plus 1 is less than 1 over n. So it is decreasing. Of course, it's alternating. The -1 to the n tells us it's alternating. The -1 to the n tells us alternating. Signs change as we go along. If you're not clear on that, -1 to the first, -1 over 1, plus 1 over 2, minus 1 over 3, plus 1 over 4, minus 1 over 5. This is the alternating harmonic. And finally, the absolute value of -1 to the n times 1 over n, which equals 1 over n, goes to 0. If all those things happen, if it's decreasing, if it's alternating, if the limit is 0, we conclude that the alternating series converges. Now, I'm noticing on the comments, someone says, can you do P series for 1 over K? That's kind of a good question. Personally, I'm not a big fan of calling that a P series question. I like to go ahead and compare it to an integral or compare it to that sum. But yes, I don't think it's a terrible thing to call it P series. But know that, please know that the sum of 1 over K diverges, call it the harmonic series, and that will be that. All right. Our next question on my first day of broadcasting. Here we go. F of 2 is 1. F prime of 2 is 3. F double prime of 2 is 9. F triple prime of 2 is 27. And the goal is to find a third order Taylor polynomial centered at 2. So let's make sure we know what that means. Taylor polynomial of order 3. I like to say A0 plus A1 x minus 2 plus A2 x minus 2 squared plus A3 x minus 2 cubed. So that's a Taylor polynomial of order 3. Order 3, highest power is 3, centered where? Centered at 2. Now, if you plug in 2, T3 of 2, that 0, that 0, that 0, you get A0. And what's F of 2? F of 2 up here is 1. Therefore, A0 is 1. Circle that. Let's take the derivative of T3. That will be A1 plus 2, A2, x minus 2 plus 3, A3, x minus 2 squared. T3 prime at 2, that 0, that 0. So I just get A1. F prime of 2 was 3. So A1 is 3. Continuing with this, next move, T3 double prime of 2, or of x, excuse me. T3 double prime of x will be equal to 2A2 plus 6a3x minus 2. So T3 double prime of 2, that goes away, gives me 2a2. F double prime was 9. F double prime of 2 was 9. So 2a2 is 9. A2 is 9 halves. And we've got one more of these to do. How about T3 triple prime of x? That is 6a3. So T3 triple prime of 2 is 6a3. F triple prime of 2 is 27. So 6a3 is 27. Let's divide by 6. Let's divide by 6. A3 is what? 9 halves? 2 times 3 is 6. 9 times 3 is 27. Okay, make sure we can see that. So we have all of our coefficients. And here is our standard approach. A0 plus A1x minus 2 plus A2x minus 2 squared plus A3x minus 2 cubed. We will plug all of those coefficients into that formula to go ahead and get our third order Taylor polynomial for this function. What will that be? Take a look. We will have, looking for the top of my paper, there we go. We'll say T3 of x A0 plus A1x minus 2 plus A2x minus 2 squared plus A3x minus 2 to the third. That's a Taylor polynomial of order 3. We solve for those four coefficients. T3 of x A0 was 1 plus A1 3 times x minus 2 plus 9 halves times x minus 2 squared plus another 9 halves. Ah, that's interesting. I didn't notice that before. X minus 2 cubed. So I hope that's right. Yes, I will upload this to YouTube by the time I'm finished with it. That's the plan, at least. So what are we going to do? The next thing we're going to ask is approximate f of 1. So to approximate f of 1, we're going to plug in 1 into your T3 function. So what is T3 of 1? 27/6, Martin. If you divide the top, 27 divided by 3 is 9. 6 divided by 3 is 2. So I think I'm good. Approximating f of 1. Halves times 1 minus 2 squared plus 9 halves times 1 minus 2 cubed. And we have some computation to do. Help me with this. Doing this at night's not my favorite thing to do. 3 times negative 1 plus 9 halves times negative 1 squared plus 9 halves times negative 1 cubed. 1, 3 times negative 1 minus 3 plus 9 halves minus 9 halves. I guess by the time all is said and done, I get negative 2. So I hope that's right. Okay, so that was using a Taylor polynomial to approximate the value of a function. So that's our story there. Question 5 on this old exam was an improper integral. So we're not going to do that on our exam. So there's no reason for us to worry about that one. But let's take a look at number 6, which is going to require us to do a test. So let me ask you guys to post the following in comments. Which test should I use to prove whether the following converges or diverges? Prove whether the following converges or diverges. And what I have is I have the sum as k goes from 0 to infinity of 4 to the n over n factorial. Which test should we use? Well, even before I ask the question, everyone's got it up there. Indeed, it is the ratio test. So we're going to proceed by the ratio test. So I need a sub k plus 1, or I guess in this case we'll call it absolute value of a sub n is 4 to the n over n factorial. And the absolute value of a sub n plus 1 will be 4 to the n plus 1 over n plus 1 factorial. And I need to look at the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Remember, if we get a limit that is less than 1, we can claim that the original converges. With the ratio test, if the limit is less than 1, we're going to get that idea. Comment says, how do you know to use the ratio test? Big hint, factorial. If you see a factorial, you almost have to use the ratio test. So let's go ahead and do this. This is the limit as n goes to infinity of this piece divided by this piece. So I get 4 to the n plus 1 over n plus 1 factorial divided by 4 to the n over n factorial, which will in turn become the limit as n goes to infinity of 4 to the n plus 1 over n plus 1 factorial times invert and multiply n factorial over 4 to the n. Now you got to think about this a little bit. Limit as n goes to infinity. 4 to the n plus 1 divided by 4 to the n. The bases are the same. Subtract the exponents. N plus 1 minus n just gives me 4. So upstairs I am left with 4. Now focus on the n factorial, n plus 1 factorial. N plus 1 factorial means n plus 1 times n minus 1 times n minus 2, dot, 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 3, 2, 1. N factorial, n minus 1, n minus 2, dot, 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 3, 2, 1. They're exactly the same, except there's an n plus 1 on the bottom. Now I get the limit as n goes to infinity of 4 over n plus 1. LA Woman says the limit is 0, and I agree with LA Woman. Indeed, that's going to be 0. If we get 0 by the ratio test, we recognize that 0 is less than 1. So we conclude that the original series converges by the ratio test. So that's our story with that one. All right. Let us take a look at our next example, which is another series. We've got to decide whether it converges or diverges. Why do we multiply by the reciprocal? Because we are dividing, indeed. Absolute value a sub n plus 1 divided by a sub n. This guy divided by that guy. Multiplying by the reciprocal is the simplest way I know to go ahead and divide those fractions. All right. Our next question is as follows. We want to prove whether this converges or diverges. And this time we have the sum as k goes from 0 to infinity of 4 plus k squared over k cubed plus 2k minus 7. Okay, so the question I have for you is, which test should we use? So we have a few different tests. Which test do you think makes the most sense? Looking on the comments, I'm seeing comparison test, I'm seeing limit comparison test, I'm seeing limit comparison test. Indeed, that's what I'm going to use. Use the limit comparison test. I think that's safer than the direct comparison test. If you have a choice of the two, the limit comparison test is typically better. The highest power on the top is k squared. The highest power on the bottom is k cubed. So that's what we're going to compare it to. K squared divided by k cubed is 1 over k. That will be the second thing we're going to compare this to. So I will say that a sub k is 4 plus k squared over k cubed plus 2k minus 7. I want you to notice when k is 1 and when k is 2, the bottom is negative, and that might bother you a little bit. But once k gets to 3, it's positive forever, and the top is positive forever. So a sub k is always positive eventually. So that's good enough for the conditions of the problem. B sub k is 1 over k. What we want to look at is we want to look at the limit as k goes to infinity of a sub k over b sub k, which will be the limit as k goes to infinity of this guy divided by that guy. So we're looking at playing with the reciprocal again. I like to use that line with the 2 dots. So I'm going to say 4 plus k squared over k cubed plus 2k minus 7 divided by 1 over k, which will then be the limit as k goes to infinity of 4 plus k squared, k cubed plus 2k minus 7 times k over 1, which will be the limit as k goes to infinity. 4 times k is 4k. K squared times k is k cubed over k cubed plus 2k minus 7. Now, you could do this formally, but I argue it's obvious that the limit of this is going to be 1. The top is a polynomial of order 3. The bottom is a polynomial crossing out the lowest terms. I get k squared. Excuse me, I get k cubed is the highest power on top. I get k cubed is the highest power on the bottom. K cubed over k cubed is just 1. 1 is not good for ratio test, but 1 is good for limit comparison test, because 1 is more than 0 and less than infinity, so the limit comparison test applies. And what that tells us is both series are of the same type. So both series are of the same type. Then what can we say? We had a sub k is 4 plus k squared over k cubed plus 2k minus 7. B sub k is 1 over k. The sum of 1 over k diverges. That is the harmonic series, or you're calling it the p series. I guess I could live with that. But the harmonic series diverges. So our conclusion, both series are of the same type because, again, the L was 1 and 0 is less than L is less than infinity. My conclusion is that the sum of 4 plus k squared over k cubed plus 2k minus 7 also what? Also diverges by which test? Also diverges by the limit comparison test. All right. Let's see what we have next. We are looking at the sum of k squared over the k squared. And we're going from 1 to infinity. And which test do you want to, excuse me, now you can see it. Which test do you want to do here? Do you want to try direct comparison test? Do you want to try limit comparison test? Which test would you like to try? Any suggestions? I am checking the comments. You want to try ratio test? Okay, we have 4 votes for ratio test, 2 votes for direct comparison test. L'Hopital, 3 to the k squared is growing faster than k squared, so I believe this is going to 0, so the divergence test isn't going to help us. Is it geometric? I don't think it's geometric. I mean, we can look at some terms. If k is 1, we have 1 squared over 3 to the 1 squared, so that's a third. K is 2, 2 squared over 3 to the 2 squared, which is 4 over 3 to the 4th, which is 4 over 81. 1/3. 4 over 81. Interesting. So I'm seeing direct comparison test coming in. We're skipping number 5 because number 5 is an improper integral that was done on our last exam. So yeah, so what can we do with this? Are these things smaller than something that we know? I mean, that's a possibility. We certainly could play the ratio test game. So maybe I'll try the ratio test first. So we'll say a sub k is k squared over 3 to the k squared. We'll say a sub k plus 1, k plus 1 squared over 3 to the k plus 1 squared, which is k squared plus 2k plus 1 over 3 to the k squared plus 2k plus 1. And if we're doing ratio test, it's this guy divided by this guy. So we'll take the limit as k goes to infinity of absolute value, a sub k plus 1 over a sub k, which is the limit as k goes to infinity, k squared plus 2k plus 1 over 3 to the k squared plus 2k plus 1 divided by k squared over 3 to the k squared. Okay. And the algebra is a bit of a mess, as so often happens in these problems. But let's go ahead and multiply by the reciprocal, invert and multiply, make sure we can see it. So if I multiply by the reciprocal, I get the limit as k goes to infinity, k squared plus 2k. Nah, try that again. That's too sloppy. Limit as k goes to infinity of k squared plus 2k plus 1 over 3 to the k squared plus 2k plus 1 times 3 to the k squared over k squared, which will be the limit as k goes to infinity, k squared plus 2k plus 1 over k squared. That limit is going to be what? That limit is going to be equal to 1 times the limit as k goes to infinity of 3 to the k squared over 3 to the k squared plus 2k plus 1. You'll recognize same base here, subtract the exponents. I'm left with 3 to the 2k plus 1 downstairs. So this first limit is 1 times the limit as k goes to infinity of 1 over, subtracting the exponents, I have 3 to the 2k plus 1 downstairs. And as that gets large, 3 to a very large number, this will equal 1 times 0, which is 0. Which again, 0 is less than 1. We use the ratio test. So the original series converges by the ratio test. Why didn't I multiply across? Simpler to go ahead and divide things out, I think. Yeah, I think you could do this in the direct comparison test, but we're a little short on time. So I think I'll pass on that. Maybe we'll take a look at that tomorrow. I'm doing a review session tomorrow at 5 o'clock. 5 o'clock in SES 250 if you want to come and see me. We've got one more problem on this thing. We're going to go ahead and find the interval of convergence for the next problem. So here we go, interval of convergence. What are we going to have? Make sure you can see it. There we go. So we've got the sum as k goes from 1 to infinity of negative 1 to the k times x minus 3 to the k over 5 to the k. And our goal is to find the interval of convergence. And it sure looks like it's going to be another problem for the ratio test. That seems to be the favorite problem on this. Yes, it is alternating. That's right. The ratio test determines whether something is absolutely convergent. Remember, if we have absolute convergence, it implies convergence. So the ratio test is a test of absolute convergence. We're going to look at the absolute value of a sub k plus 1 divided by the absolute value of a sub k. That's going to be our idea with, of course, a limit. So a sub k is what we have up there. The absolute value of a sub k loses the sign flasher. And we get x minus 3 to the k over 5 to the k. The absolute value of a sub k plus 1, again, the sign flasher is gone. I have x minus 3 to the k plus 1 over 5 to the k plus 1. So let's go ahead and take a look at the limit now. Ratio test, again, proceed by ratio test, which they certainly used a lot in spring 18. We're going to look at the limit as k goes to infinity of a sub k plus 1 over a sub k, which is the limit as k goes to infinity of x minus 3 to the k plus 1 over 5 to the k plus 1 divided by x minus 3 to the k over 5 to the k, which will be equal to the limit as k goes to infinity, invert and multiply, x minus 3 to the k plus 1 over 5 to the k plus 1 times 5 to the k over x minus 3 to the k equals the limit as k goes to infinity. Let's look at the algebra here, friends. X minus 3 to the k plus 1 over x minus 3 to the k just leaves absolute x minus 3. 5 to the k over 5 to the k plus 1, one more downstairs, which is 5. Which in turn, I can pull this out. This is not changing. K is changing. This comes out in front of the limit sign. Absolute x minus 3 times the limit as k goes to infinity of what? Everything's gone? Of 1/5? I guess so. So we get 1/5 absolute x minus 3 is our value. Now, for this to converge, that has to be less than 1. We've got to go ahead and show that that limit is less than 1. So I'm getting some radius of convergence, intervals of convergence on the comments. Looks kind of interesting. We need this to be less than 1. Need to be less than 1 to converge. Remember, it equals 1. The ratio test is inconclusive. So here's where I am. We have 1/5 absolute value of x minus 3 has to be less than 1, which means absolute x minus 3 has to be less than 5, which tells me negative 5 is less than. Add 3 everywhere. So negative 5 plus 3, negative 2 is less than x is less than 8. But we're still not finished. We're still not finished. We need to do what? We need to check the endpoints. So we know we're good from negative 2 to 8. The question is, are we good at the end? So I'm going to go back to my original question, and I'm going to name it a function. I'm going to say f of x is the sum as k goes from 1 to infinity of negative 1 to the k, x minus 3 to the k over 5 to the k. Checking the endpoints, check negative 2, check 8. What is f of negative 2? Is the sum as k goes from 1 to infinity of negative 1 to the k, negative 2 minus 3 to the k over 5 to the k, which is the sum as k goes from 1 to infinity of negative 1 to the k, negative 5 to the k over 5 to the k. Kind of interesting. Which is the sum as k goes from 1 to infinity, negative 1 to the k, and another negative 1 to the k times 5 to the k over 5 to the k. And then what does that become? Negative 1 to the k times negative 1 to the k. When this is negative, so is that. When this is positive, so is that. So this just becomes the sum as k goes from 1 to infinity of 1, which is 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, diverges. So at -2, it diverges. The other endpoint was 8. So what does f of 8 look like? Again, f of x is the sum as k goes from 1 to infinity of what? What do we get? We get negative 1 to the k, x minus 3 to the k over 5 to the k. I want 8. What is f of 8? Sum is k goes from 1 to infinity. Negative 1 to the k, 8 minus 3 to the k over 5 to the k. Sum k goes from 1 to infinity. Negative 1 to the k, 5 to the k over 5 to the k, which is the sum. K goes from 1 to infinity of negative 1 to the k, which equals negative 1 plus 1 minus 1 plus 1 minus 1. This diverges by the kth term divergence test. Diverges by divergence test. So what is our interval of convergence? The interval of convergence is simply from -2 to 8. -2 less than x less 8, written which way in this notation? From -2 to 8. So friends, that was the test that was given spring of 2018. I skipped the question on improper integrals that will not be on your exam. This exam goes up through Taylor and Maclaurin series. We didn't do any power series in this review. I don't think it was on the exam last semester. So I'll make sure to point you in the direction of my discussions on power series. I hope you found this useful. It was interesting for me. I hope the technology worked, and I will post the entire discussion on YouTube on my page, and I'll pass that on to you as well. Thanks so much. Hopefully I'll see some of you tomorrow night at 5 o'clock for our review session. Take care.